So we've done two different methods, well, really three methods for finding volume. We've done these cross sections where we were slicing things, and then we did two types of rotational volume. We had the washer method, and then we had the shell method. And those cross sectional volume problems that we did first, where we were slicing, those problems are obvious what type of problem they are, because that's where the problem will say something like cross sections perpendicular to the x-axis or squares, or cross sections perpendicular to the y-axis or triangles. They're going to tell you what the slices look like. So it's really these two types of rotational volume, where we're rotating things about the x-axis or the y-axis or some line, where we have to determine whether we can use the shell method or the washer method. And I want to go ahead and do this today so we can start making sure we distinguish when we use which. Sometimes we can use either method, and sometimes we're forced to use one or the other. So let's look at this example and then we'll see more in class. And I know we've seen a few of these already in class too. So we're going to look at this region enclosed by these two sideways parabolas. So negative y squared plus 7, that's a parabola that opens to the left because of the negative. It shifted over to the right 7 units because of the plus 7. So we're going to have 1, 2, 3, 4, 5, 6, 7. So opens to the left and shifted 7 units to the right. So this is my negative y squared plus 7. And then let's see, the other one is going to open to the right because it's positive, and it's going to be 5 units over. So that's this here is my y squared plus 5. And so the region that we're looking at here is this little guy in here. I could ask you to find the area of that region. It's kind of a fun question to ask. If I were going to find the area of this region, we would notice that we need to use horizontal line segments, not vertical line segments. And so the fact that this region itself forces us to use horizontal line segments we're going to be forced to use those horizontal line segments no matter what we're doing with this region, whether we're finding area, whether we're rotating this and finding volume. It's the region itself that determines whether we can do things in terms of X or in terms of Y. This particular region, I can only do things with horizontal line segments, because otherwise my top and bottom function would change and would be the same function. So just like when we were doing area, I'm forced to do things in terms of Y here. So all of my integrals related to this region have to be in terms of y. And now when we're rotating, we have to remember that, and that's going to kind of force things to be a shell or a washer method, because this region itself is forced to do things in terms of y. Okay, so for this first question, determine the volume of the solid that results from rotating about the line x equals 2. So the line x equals 2 is this line here. Okay, so if we rotate this region about the line x equals 2, let's take 2 pens here. So we've got our x equals 2, and then we have that little line we're rotating about. Maybe if I find a brighter colored pen here, maybe the green will stand out better. So we're rotating about that line. And so we have two things that are perpendicular to each other. When I rotate that green line segment about my line x equals 2, that green line segment is going to make a washer. Okay. And that green line segment, I'm thinking, is just one of these little lines that I've drawn up here. That's what that green is representing. Okay. So we're going to get a washer out here. Remember, we always get washers when the line I'm rotating about is perpendicular to the thing that I'm rotating, the little line segment I'm rotating. Okay, so we're going to do a washer method here. And so remember, we're going to have things in terms of y. The washer method is going to have an inner radius squared, outer radius squared minus inner radius squared, to get these in the right direction. Okay, so my outer radius is the distance from the line I'm rotating about to the second function that I bump into, which is going to be that black function. Okay, so as always, I do right minus left if I'm doing things in terms of y. So for my outer radius, my rightmost function is that black curve, so negative y squared plus 7. So that's my right, minus left is that blue function, which is x equals 2. So we're going to subtract 2 from that. Okay, minus my inner radius is what I bump into first, which is the red curve. So if I do right minus left here, I'm going to do right curve or red curve minus blue curve. So the red curve is y squared plus 5 minus blue curve is 2. We have a dy. Notice I still need to know the bounds on this integral. The bounds are not determined by what I'm rotating about. They're only based on the region itself. So I could have found the bounds before I even started answering this part of the question. So the bounds are going to be these two values. Okay, so I just need to know where these curves intersect. So I need to set these two functions equal to each other. Those are going to be kind of messy, not terrible, hopefully. So let's see, if I add y squared to both sides and subtract 5, then I get 1 is y squared. When I take the square root of both sides, I get a plus or minus. So y is plus or minus 1. So this down here was y equals -1, and this is y equals 1. So I integrate from -1 to 1. Okay, notice those bounds come from the region. They don't come from what I'm rotating about, okay? So this region itself, this little yellow region that I've shaded, the bounds on that region are always going to be -1 and 1, whether I'm finding the area, whether I'm finding a volume, no matter what I'm rotating about here. So there's a few key things to think about, that the region itself dictates whether I do things in terms of x or in terms of y, and what the bounds on the integral are. These come from just from the region, not from what the problem is asking us to do. Okay, so let's do the second question. So y equals 3 is up here. Okay, so we know that this region is going to force us to do things in terms of y, and that my bounds are going to be -1 to 1. Doesn't matter what I'm rotating about. That's all just based on this region. Okay, and so now we have to figure out what method we're using. So we're taking our line y equals 3, and we have our little horizontal line segments. We're rotating about that. So if we take one of those green lines, remembering the green line is one of those guys inside of the region. So if I rotate that about a horizontal line, that's going to give me a shell. I think that's kind of like the outside, like, it's giving me like a whole shape like this. So that's a shell. So we're getting a shell here. Remember, anytime our lines are parallel to each other, we get a shell. I think parallel has 2 L's, shell has 2 L's. That's how I remember it. So we are going to use a shell method here. So shell method has a 2 pi, a radius, and a height. Okay, in this case, our shells are sideways like this. So the height is this length. The height is the length of that little line segment inside of my region. That's just a right function minus left function. So my height is, let's see, what is the right function in this case? The right function is the black one. So negative x squared plus 7 minus the left function, which is the red one, y squared plus 5. Remember, put that y squared plus 5 in parentheses. Okay. Now my radius is the distance from the line I'm rotating about to one of those little line segments. So that's this distance here. Okay. Well, and not all the way down to the x-axis necessarily. So I go from some arbitrary y value to the line y equals 3. We always do top minus bottom or left minus right. In this case, I have a top and a bottom. The top is 3, and the bottom is just some arbitrary y value. So I get y minus 3, and we have a dy. Okay. Notice I didn't compute either of these integrals. I just set them up. You could go ahead and type these in a calculator. They'll be like vaguely messy to compute by hand, although also totally doable.